Today we'll talk about nonlinear classification. We've seen how linear classifiers can be learned, but those can be easily extended to nonlinear classifiers, and we will see how to do that today. At the core of the idea is expanding the feature representation that is fed to a linear classifier. And we will talk about feature maps and how they enable nonlinear classification. Expanding feature maps into very high dimensional ones carries a computational disadvantage, and we'll show how you can avoid that by using something called kernel functions. And we will then generalize our linear methods to kernel methods, in particular considering for simplicity just kernel perceptron. And briefly towards the end, we'll also look at some other nonlinear classifiers. Let's consider a very simple case here on the real line. X here is just a real number scalar. And we are trying to do linear classification of examples represented by features as real numbers. So for example, I can put two examples here along the real line. One labeled -1, the other one labeled +1, and maybe this is at the point x equals 1. We can easily classify this example correctly using a linear classifier. Remember that the linear classifiers were represented as 8, taking x, the example, as an input, and having two parameters, theta and theta naught, where now both of these are scalar since x is one-dimensional. And this is just a sign of a linear function here. Now just a regular scalar product of theta x plus theta naught. Okay? Now we can take the argument to the sine function and plot that as a linear function of x. So this is now theta x plus theta naught. Notice that this is not, this isn't boundary. This is the argument to the sine function, which is a linear function of x. It takes positive values here in the realm where x should be classified positively, and it takes negative values in the regime where x should be negatively labeled. Okay, so it correctly classifies these two examples as seen here. If we add one more example here, let's say at -1, and label that also positively, then our linear classifier no longer classifies these examples correctly because it takes negative values here, take the sign, and we would predict -1 as the label. Notice that there is no linear classifier that can solve this problem, not only that this particular one doesn't. We can remedy the situation by introducing a feature transformation, feeding a different type of example to the linear classifier. So for example, we map x now to a feature vector, phi of x. So remember that x here is a scalar. Feature vector now lives in a high dimensional space, and we will put x here. We will always include in these feature vectors the example itself, so as to be able to retain the power that was available prior to feature transformation. But we will also add additional features here, such as x squared. Okay, so phi of x now lives in R squared. As a result, our theta, that used to be scalar, now theta has two coordinates, theta 1 and theta 2. Okay, so after this feature transformation, we will feed those transformed examples to the linear classifier as if they were the examples to begin with. So as a result, our new classifier takes x, scalar x as an input here, theta and theta naught. Now theta is a two-dimensional vector, and it is sine of now theta dot in a product with the feature vector corresponding to x plus theta naught. Okay, so if we expand this, this would be sine of theta 1 x plus theta 2 x squared plus theta naught. So we threshold a quadratic function rather than a linear function in this case. But our classifier here thinks of these feature vectors as the examples, so operationally everything can work out as before. Let's look at this now in a feature coordinates. So we have two coordinates, phi 1 and phi 2. Remember that phi of x is now x and x squared. So the first coordinate here is the phi 1 coordinate, second coordinate is the phi 2 coordinate. So all the examples that we will see as they are mapped into the feature coordinates lie on this little parabola. Our negatively labeled example that were at the origin, x equals 0, now maps to the origin in this two-dimensional space. Example that was positively labeled at x equals 1 now maps to feature coordinates here 1, 1. And similarly, the example that was at -1 now maps on to feature coordinates corresponding to -1, 1. These examples that previously were not separable are now easily separable by a linear classifier in this space. For example, this one. All the examples, as they are mapped to feature coordinates, they now include more information about x that's more explicitly linearly accessible, and we can separate those examples in these feature coordinates, thinking of linear classification now in the higher dimensional space. Let's look at what this implies back in the original x space. Okay, so I will now mark those examples again here in the original scalar x space here. We have an example at -1, 0, and 1. And this is positively labeled, negatively labeled, and positively labeled. Okay? So now our classifier here is no longer a linear classifier in the original space. It is a nonlinear classifier because we performed a nonlinear feature transformation. So remember that it's now quadratic, thresholding a quadratic function. And we can plot this quadratic function here now, like so. So this is again not a decision boundary. Decision boundary lies exactly 2 points here in 1D, where the decision changes. And you can notice that this quadratic function, as we are thresholding it, it takes positive values here correctly, classifying this example correctly, takes negative values in this interval, classifying this correctly, and again takes positive values in this regime, classifying this example correctly. All right. So a linear classifier in the new feature coordinates implies a nonlinear classifier in the original X space. Let's take one more example here. I have now X that lives in two-dimensional space, and I've plotted here 4 points that are not linearly separable. So we cannot find a linear classifier in the original x1, x2 coordinates that would correctly classify these examples. But I can map this now into a high-dimensional space. So I will now introduce feature transformation phi of x. X is 2D. That has the original example as the first two coordinates. Remember, I will always want to retain the information I had before so as not to lose any power. But then I will add an additional feature coordinate here that's just a product of the two original coordinates. Okay? Our parameter vector theta, used to live in 2D, now has 3 coordinates, theta 1, theta 2, and theta 3 associated with the coordinates of the feature transformation. Okay? And we also have the offset parameter as before. Let's now map these examples, these 4 examples, onto the feature coordinates, the new higher dimensional feature coordinates. I can draw the phi 1, phi 2 plane here, where the examples previously lied, x1 and x2. And they lied in these corners, but now you can see that based on the last coordinate of the feature transformation, the positively labeled examples have coordinates that are all positive for 5, 3, and negatively labeled examples have negative values for that coordinate. So the positively labeled examples are now lifted upwards. They live here phi 1, phi 2. So this corner here is positive. That gets lifted up a little bit here. It's a positively labeled example. The other positively labeled example is here. It's lifted up based on its phi 3 coordinates here. And now the negatively labeled examples are put down by 1 and live a little bit lower in this higher dimensional, 3-dimensional space. Okay? Now you can see that the phi 1, phi 2 plane is actually an appropriate way to separate these two examples. Okay? As a result, you can easily verify that the theta that now points upwards, orthogonal to the decision boundary, which is a plane in 3D, can be just selected to be 0, 0, 1. So we make decisions only based on the last coordinate, and theta naught can be 0. So this, as an estimate, would correctly classify those examples now in the higher dimensional feature representation. We can play this game further for any example x. Let's say it's a scalar. Again, we can add feature coordinates, not just a single one, but we can take x, x to the power of 2, 3, 4, and so on. We can always add additional feature coordinates here. And we will get more and more powerful feature representation, more and more powerful classifier operating linearly in these expanded feature vectors. Now, adding these features results in more and more features if x is already higher dimensional. So when x is actually 2-dimensional, okay, so it lives in R2, then if we just include the second order features, we will get a lot more here. We will get the example itself, x1 squared, x2 squared, and then also the cross term x1, x2, and we could multiply that with a scalar whose meaning will become clear later. Okay, so now the new feature vector lives in 5-dimensional space. Okay, so we can get more and more powerful classifiers by adding linearly independent features. So x and x squared as functions are linearly independent, so the additional coordinates always provide something above and beyond what were in the previous ones. So adding more of these coordinates will always result in a more powerful classifier. Okay, so now by mapping examples into a feature representation and performing linear classification in the new feature coordinates, we get a nonlinear classifier. We can do the same thing for regression. Here I have a regression function, first map example into a feature vector, and then do linear regression in the feature coordinates. As a result, let's say 5x is just a second order expansion, then our regression function now would be a quadratic function. So a linear regression based on x and the output y cannot capture relationships like this, but if we map to the second order features, the regression function that we are actually estimating in the original space is a quadratic function like this that can capture that easily. All right, so now we can always introduce more and more complicated feature transformations. If it's linear, then the feature transformation is identity. If it's third order here for one-dimensional regression, feature transformation would be here x squared, x to the power of 3, and so on. More and more features we include, more powerful regression method we will get as a result. Okay, and up to 7th order, it fits perfectly these data points. So one question here is, which one of these should we actually choose? Which one is the correct one? We get more and more powerful regression method, but we don't know which one is correct. We fit the training data better and better with more features. So what we can do, as we've discussed before, is to introduce, say, a validation set. Hold out some subset of examples, train the method based on the remaining samples, and then try out those held out examples to see how well the method would actually perform on those pretend test examples. At the extreme, you hold out each of the training example in turn in a procedure called leave one out cross-validation. So you take a single training example, you remove it from the training set, retrain the method, and then test how well you would predict that particular held out example, and do that for each training example in turn, and then you average the results. Okay, so if we take the 7th order polynomial regression method here and hold out this particular example, train the method, and then test how well we would predict its value, we would probably get a pretty good answer. Okay, so the error on that example, if it were held out, would not be a lot. But if you hold out this one, the corresponding regression function would change quite a bit, and as a result, you would get a drastic error for that held out example. So you could not correctly predict that unless it were part of the training set. Okay? If we now use this leave one out accuracy as a measure of selecting which one of these is the correct explanation, we would actually select a linear one. That is the correct answer because the data was generated. I know how it was generated, and it was generated from a linear model with some noise added. All right. So the downside of this procedure, which is always available to you, is that you might end up with a very high dimensional feature vectors that you have to explicitly consider. So, for example, if we take now a feature transformation and X already lives in RD, where D could be, say, 10, 100, then the corresponding feature vector would have first order features, the original example here, exactly as before. We get order D features from that. If we add all second order features, we will add all feature products. And there are D squared such features on the order of D squared. We add all third order features as well. We get three-way products of all the coordinates. And we get D squared features and so on. So our feature vector becomes very high dimensional very quickly if we even start from a moderately dimensional vector. Okay? So we would want to have a more efficient way of doing that, operating with high dimensional feature vectors without explicitly having to construct them. And that is what kernel methods provide us. Okay? The idea is that you can take inner products between high dimensional feature vectors and evaluate that inner product very cheaply. And then we can turn our algorithms into operating only in terms of these inner products. So let's see how this is possible. If I have two feature vectors here corresponding to two different examples, x and x prime, and now I evaluate the inner product between these two feature vectors. Okay, I multiply the coordinates, corresponding coordinates together and add them. The first part here is just in terms of the original two-dimensional example. So I will get a part here that's just inner product between x and x prime as vectors. When you do the inner product of the remaining coordinates and add them, you see that it looks like a quadratic expression, and indeed it is. And you can verify that what I get there is just x inner product with x prime, and that scalar value to the power of 2. So if you expanded this, you would get the inner product that arises from these coordinates. Okay? So this inner product between two feature vectors can be evaluated cheaply based on just taking inner products of the original examples and doing some nonlinear transformations of the result. And this idea carries further. So if you add third order terms here weighted appropriately, you can add here x prime to the power of 3. So our computation of the inner product didn't get any more complicated, even though we added tons of more features to the feature vector. The calculation of the inner product is now just as easy as it was before. Okay. Now this inner product of two feature vectors is known as a kernel function. So it's a kernel function is a function of two examples, say x and x prime, and it always corresponds to an inner product between some feature vectors. So kernel really should have a subscript here that corresponds to the feature transformation so as to explicitly say what that transformation is, but that's typically left out. Okay, so this is now called kernel function. All right, and what we saw here is that sometimes, depending on the feature transformation, the kernel can be evaluated very cheaply, even though we would have to explicitly construct very high-dimensional feature vectors. All right, so what is our task now is to somehow turn our linear methods into methods that can operate in terms of the kernels rather than directly in terms of the feature coordinates. And we'll see how this is possible. If we succeed, then we can implicitly operate with very high-dimensional feature vectors and do the linear prediction there, but actually computationally only deal with the kernel functions. All right. So what we've seen here is that the kernel functions can be evaluated sometimes cheaply, depending on the feature transformation. So how efficiently we can evaluate the inner products depends on the feature vectors. For example, if it's an any order polynomial feature transformation, we can take just 1 plus x and x prime to the power of p, and p could be here 1, 2, and any order. This would be a possible kernel function that's cheap to evaluate and corresponds to the type of polynomial feature vectors that we've already discussed, up to some arbitrary order that we define. Okay, so now our task, as I said before, is to turn a linear method that previously takes theta dot phi of x plus theta naught and tries to classify that. That's our linear classifier. Somehow we wish to turn that into a classifier that only depends on those inner products, operates in terms of kernels. Okay? And we'll do that in the context of kernel perceptron, just for simplicity, but it applies to any linear method that you've already learned. Okay? So let's see how we can do that with a simple perceptron classifier. So recall that perceptron initializes the parameter vector to 0, runs through training examples multiple times, but I've only displayed here a one run through the training examples. We check if we make a mistake here without the offset parameter. Again, for simplicity, we take the training label and the linear prediction and ask whether they have a different sign. And if so, we make a mistake. And after each mistake, we perform a very simple update that simply adds a label times the corresponding feature vector, now transformed into the new feature coordinates, to the parameter vector. Okay? So after a while, after these updates, we can now summarize what is the theta, the parameter, that results from this update scheme. Okay? Every time we make a mistake, we add that little label times the corresponding feature vector. So I can summarize that by taking a sum over the training examples of how many times I performed the update on that jth training example. So this is the number of mistakes. And every time we make a mistake, we add to the parameter vector the corresponding label times the feature vector. All right. So now I've represented the parameter vector that lives in that high dimensional feature coordinate space in terms of just number of mistakes that the algorithm makes on different examples. We no longer look at explicitly in terms of coordinates of theta as parameters, but in terms of importance of training examples to the final predictor. So alpha here, because we are doing perceptron, the importance is just in terms of the number of mistakes that we make on that particular example so far. Okay? So now when we make a prediction using the resulting parameter value theta, we take an inner product with that, and an example could be a new example or could be one of the training examples. We want to make a prediction how well that parameter value now captures the classification of that example. So if we do this on this side too, we take an inner product with each of the training examples and that new example xi. So you can see that the way the perceptron algorithm would make predictions can be expressed just in terms of the kernel between the jth training example and the ith training example. If we can evaluate the inner product, then we can run the algorithm only in terms of the kernel functions, without regard to how to explicitly construct the feature vectors. So let's look at the cleaner version here. So what we've seen so far is that the parameter vector theta, how it makes predictions, can be written as a sum over the training examples multiplied by how many times we made a mistake on that example, corresponding label, times now the kernel function between the jth example and the ith example. Okay? So we want to now express that algorithm in terms of the kernel values and the mistakes that we make. Okay, so initialization, theta is all 0. That means we haven't made any mistakes so far. So the corresponding initialization in terms of alpha is just to set all the alphas, 1 alpha for each training example, and set them all to 0. Okay, then we run through the training examples. When we test whether it's a mistake, we have to construct that prediction, which we've now expressed in terms of alpha and kernels. So we ask whether the ith label times this sum now over the training examples, how many times so far we've made a mistake on the jth example, its label times the kernel evaluated between the jth and ith training examples. And if this is now negative, 0 or negative, then we make a mistake and we need to perform an update. Now, update is very simple because the alphas count how many times we've made this particular update. So here we would simply say that we increment alpha I by 1. Okay? So now we have an algorithm expressed in terms of number of times we make a mistake. We've expressed predictions in terms of the kernel functions and the alphas. And we have a very simple update equation. Okay? I will tell you what the kernel function is. Then I can run the perceptron algorithm and implicitly operate in that higher dimensional feature representation, while running the algorithm only in terms of the scalar valued kernel evaluations between two examples. Okay? So you can think of the kernel function here as a kind of similarity measure. How similar the jth example is to the ith example. So our predicted value here is now how important the jth example is, its label times how similar the example we wish to make a prediction on and the jth training example is. All right, that is now the kernel perceptron algorithm. Now, instead of directly constructing feature vectors by adding coordinates and then taking in a product and seeing how it collapses into a kernel, we can construct kernels directly from simpler kernels. So here are simple composition rules for kernels. A simple constant one is a kernel function. The corresponding feature representation is simply that phi of x is just 1. And if you take an inner product of 2 feature representations, then clearly you get 1 for every evaluation. If you pre and post multiply a kernel by any function, scalar function f of x, so kernel is evaluated between 2 examples. So you multiply that kernel with a f of x and f of x prime, the resulting thing is also a kernel. So if I had feature vector phi of x before corresponding to this kernel, then the new kernel has a feature vector phi twiddle that's just that function, scalar function multiplying all the coordinates of the previous feature vector. Okay? If I have 2 kernel functions, k1 and k2, so they have their own feature representations. If I add the 2 kernels together, I will get a kernel, valid kernel function that now has a feature representation that's just a coordinates appended from the 2 previous kernel functions. And if you take an inner product between these 2, you see that you get 2 inner products, one with respect to the phi 1 representation, giving k1, and added to that is the inner product between the feature vectors corresponding to phi 2. And similarly, you can verify that if you take a element-wise product, so a simple product, since kernel evaluated at any 2 points is a scalar value, you can take a product of the corresponding scalar values corresponding to 2 different kernels, and as a result, you also get a kernel value that has an associated feature vector that's now constructed on the basis of the 2 feature vectors corresponding to these kernels, and so on. So this is actually a comprehensive set of rules from which you can construct the kernels that we already saw. So remember, for example, that in our earlier case, we had a kernel that's just an inner product with the original examples. That's called a linear kernel, where phi of x is just identity. We can add to it a squared term, and to verify that this resulting thing has a feature representation, this squared now is a product of 2 kernels, identical kernels. You get that kernel value squared, and you add here 2 kernels together, then according to the 3rd rule, you get a valid kernel as a result, and so on. All right, so now let's take a more interesting example to illustrate the power that you get from incorporating kernel functions. Okay. Now you can show that this here called radial basis kernel is also a kernel function, and it can be constructed from those composition rules that we saw before, but we'd actually have to compose that infinite number of times, since this has a feature representation in terms of vectors that's infinite dimensional. So you could not possibly operate in terms of those feature vectors explicitly. Yet you can evaluate their inner product nicely, compactly, in terms of just taking the squared Euclidean distance between the corresponding training samples, negate and multiply by half, and take exponent of that. Very simple to evaluate for any two examples, x and x prime. Okay? So intuitively, what this looks like in the, say, x1 and x2 coordinates, the kernel is a little bump here. If we center it at x and look at how does the kernel evaluate if we change x prime here, then you would get this decreasing values, a little Gaussian bump centered at x. And so the further x prime moves away from that x, the more rapidly the value of the kernel, or the similarity measure here, decreases. And when you move really far away, it's nearly zero. Okay? Now, since this kernel function, radial basis kernel, involves polynomial features up to infinite order, it is actually infinitely powerful. Okay? So, if we have any distinct set of training samples, then a simple perceptron algorithm operating with these kernel functions, which is easy to do based on the algorithm that we've already seen, would correctly classify all of the training samples. Okay, so let's see how that works. Here I have that simple example with red examples here negative and blue pluses here. And we find a decision boundary that now correctly classifies these training samples, and the boundaries learned by applying just the simple kernel perceptron algorithm. So the decision boundary here, now mapped into the original coordinates, it is a linear boundary in that infinite dimensional space, but mapped into an original space, it looks like a nonlinear boundary, and it is just all x such that now the sum over the training samples, how many number of times that we've made a mistake, label of that example, and kernel function evaluated between the training example and a new example x when this is 0. So all x that satisfy this equation now define the linear decision boundary in that infinite dimensional space, but it's clearly a non-linear boundary in the original space. Okay? And all we learn is we specified the kernel function as the radial basis kernel. So for any 2 points, easy to evaluate what the value of the kernel is. And all that we need to learn are the alphas, running the perceptron algorithm and seeing if we make a mistake, and we increment alphas by 1. Okay? So let's apply this method to a more complicated task. We moved the positively labeled points a little bit. Based on what I said, we should be able to correctly classify these as well. And indeed, we find a decision boundary that correctly separates these two. Even if we make that task quite difficult, see here, examples are quite close with the intervening negative examples and so on. Based on what I said, we should be able to run simple perceptron algorithm using this kernel function and correctly classify these points on the training set. And indeed, That is what happens. The more difficult task it is, it may take a little more iteration before this kernel perceptron with the radial basis kernel finds that separating solution, but it always will. Okay? So previously we discussed how perceptron algorithm was limited because when it couldn't correctly separate the training samples, we didn't know exactly when to stop that algorithm. It would continue changing the parameters. That's no longer the case if you use the radial basis kernel. It will halt after a finite number of steps. All right, so far we've seen a paradigm where we map examples to feature vectors that include nonlinear terms in order to get a nonlinear prediction method. And then we can collapse those calculations using kernel functions to operate implicitly in those high dimensional space. Now, there are certainly other ways to get nonlinear classifiers. For example, a decision tree simply makes cuts here in that coordinate space, axis parallel cuts. So, for example, it would be able to separate examples in this way. So first, it asks whether, say, here, x2 coordinate is less than 1 or it's greater than equal to 1. Let's say this is 1 here. And going further, if it's greater than 1, it wants to split the data again into two regimes. Here, maybe the value is 2. So if x1 is less than 2 and x1 is greater than equal to 2. So in the two cases, it would now predict different labels here, and you get a decision tree that trickles the example here based on those comparisons into the right bucket here, and then spits out the answer. And you can learn these trees incrementally. A more robust procedure is something called a random forest that generates multiple versions of this tree by controlling which coordinates can be used as a split as you're building the tree. That introduces one set of randomization. The other randomization is by drawing a bootstrap sample of the training example, drawing n examples with replacement from the training set, so as to create some variability also of the data from which the trees are generated, and then you just average the predictions from this tree. That's called a random forest classifier, and it is quite robust prediction method. And there are many other alternatives for nonlinear prediction as well that we will not go through here. All right, so in summary, what we've seen is that we can take a linear method and operate just with the linear method so long as we map the examples into nonlinearly into feature representations, and we get a method that's much more powerful. And we can collapse those computations by operating implicitly in the feature representations with the help of kernel functions. And one kernel function, radial basis kernel, is particularly powerful because it is easy to evaluate, but it corresponds to infinite dimensional feature vectors that we could not operate explicitly, but we can operate through the kernel function quite well.